All right, and this part isn't really anything that's too new for us either. So we can be given a discrete random variable and its distribution, and we can calculate a mean from it. So this is similar like what we did with group data, but it's a little closer to what was a weighted mean. So the mean of a random variable, like I said, think about this as more like a weighted mean, but really like it's not too different from other kinds of things that we call it. One of the other things we're going to call it is an expected value. Recall that the mean is a measure of center. The mean of a random variable provides a measure of the center of the probability distribution of a random variable. So another name for the mean of a random variable is called expected value. So expected value is the idea. So usually using this for things that we're talking about gains and losses, and we're talking about an overall loss or an overall gain. And a lot of this is going to be involved, a lot of times money is what we use when we're talking about expected value. So to find the mean of a discrete random variable, multiply each probability value by its probability, then add the products. So if you remember with a weighted mean, what we did is we did the sum of our variable times its weight, and then we divided by the weight, the sum of the weights. So this isn't too different because we did an example of this where we did percentages. So in that case, we did percentages and then we had it over 100. So this is going to change a little bit if they, instead of doing percentages as whole numbers, we talk about probabilities as the decimals. This just changes a little bit here. So all we do is we take each value and multiply it by its probability, which is its weight. So a probability is just your weight compared by the sum of the weights. So it's not really that much different. This is still just doing a weighted mean. But all we're going to do is take x times this probability and sum those together. So a computer monitor is composed of a large number of points of light called pixels. It is not uncommon for a few of your pixels to be defective. You might not even notice it for the most part, but it's possible that you have a couple that are going to be dead pixels. So we're going to let x represent the number of defective pixels on a randomly chosen monitor. The probability distribution x is as follows over here. We want to find the mean number of defective pixels. So we're saying that a monitor, like maybe a brand new monitor, this is what we're expecting to find. Either we have no dead pixels, 1, 2, or 3 dead pixels. The probability that my new monitor would have 0 dead pixels is 20%, that at least 1 is dead is 50%, that 2 are dead is another 20%, and that 3 are dead is 10%. I want to figure out what is the mean number of dead pixels I can have. So all we have to do to figure out what this mean is I just need to take each value, each x, each random variable, and multiply it to its probability, and then sum them up. So if I do that, I have x times my 20%. We're going to use a little symbol like that. That is going to be 0 there. 1 times my 50%, that's 0.5. My 2 times my 0.2, that is going to be 0.4. And my 3 times my 0.1 is going to be 0.3. So the summation of all those is just going to be 0 plus 0.5 plus 0.1 or 4 plus 0.3. So that is going to add up to 5, 6, 7, 8, 9, 10, 11, 12. So that is 1.2 defective pixels. Which you see right here. So like I said, because it's a weighted mean, it's not exactly in the center of my distribution, it's here. I remember these are values that kind of like, we're looking at like a combination of weights and the actual number that we have. So we're kind of just looking for that place where everything balances out. So the only thing that changed here is I wasn't dividing by the sum of my frequencies or the sum of my weights or anything like that. And that is just simple because I don't need to do that, because when I have that probability, that sum of my frequencies or my sum of my weights was already put into that calculation. Okay. So law of large numbers. If a probability experiment that produces a value of random variables is repeated over and over again, the average of the values produces the average of the values produced will approach a mean of the random variable. So when the probability experiment is sampling from a population instead, then the interpretation of the mean says that the sample size increases, the sample mean will approach the population mean. So we had mentioned this before, that larger sample means are better approximators of, or larger samples are better approximators of population data. This is known as the law of large numbers for means. So it's the same idea. If I repeat experiment over and over and over again, and I do an average of all those experiments, that is closer to the true average of that random variable. If I get larger and larger sample sizes, that's the same thing as like doing several trials. Larger sample sizes, kind of along that same idea, that the values that I get, like a sample mean, will be closer to a population mean. So the law of large numbers of means is if we sample items from a population, then as the sample size grows larger, the population mean will approach the sample mean will approach the population mean. Okay. So this is going to get us into expected value, because expected value is trying to predict what happens in the long run or what happens to a population. There are many occasions in which people want to predict how much they will gain or lose if they make a certain decision or a certain action. Often this is done by computing the mean of a random variable. In such situations, the mean is sometimes called the expected value, and it's denoted by EX. If the expected value is positive, it is an expected gain, and if it is negative, it is an expected loss. And this is going back to the law of large numbers, is that expected values are really looking at long term. They're looking at multiple times of repeating an experiment over and over and over again, or collecting more and more data. So do not apply expected values to like one-off situations. It's not a good predictor of that. A mineral economist estimates that a particular venture had probability of 40% of a $30 million loss. So most likely they collected several samples of similar kind of ventures to kind of get an idea of what the loss would be. We have a probability of 50% that will have a $2 million profit or $20 million profit, and a 10% chance of getting a $40 million profit. We're going to let X represent the profit. We're going to find the probability distribution of the profit and the expected value of the profit. Does this venture represent an expected gain or loss? So the idea probably is that you are going to invest $30 million, and if this venture doesn't work right, you lose the money. If it goes okay, you might make 20 billion back. If it goes well, then you're going to be in a surplus. You're going to have made like this much back. Okay. So my X's are going to be represent the profit or loss that I have. So losing 30 million, that's a negative 30, and that has a probability of 40%. 20 million, that's a net gain of 20 million, that is going to have a probability of 50. A net gain of 40 million is going to be a probability of 10. So if I want my expected value, it's the same thing as finding that weighted mean. It's just going to be the summation of my X's times their probability. So here we're going to have X times P of X. So negative 30 times 0.4, I believe that is going to be negative 12. Here we got 20 times 0.5. So that will give us a plus of 10. And then my last one is 40, and then times my 10%. So that is going to be a plus of 4. So all I have to do is just add that up. Negative 12 plus 10 plus 4. So this is going to end up giving me 2 in the end. So my expected gain because I'm gaining here is 2 million. So this is really an average. And the way to really think about this is that if we're looking at similar ventures and you are putting in money into these ventures, so like let's say you have this tons of money you can invest, and you keep investing in several different ventures that are very similar to this, we're expected that in the end, if I do this enough times, basically an infinity number of times, it should be gaining $2 million. So this is kind of like a way to judge, like, do I really want to take a chance on doing this? Like, if I'm into investing, do I want to invest into, this is a mineral economist, do I want to keep investing into these mineral ventures when what I'm looking at is that probably in the end, after doing tons and tons of it, I only get a net gain of $2 million. But that, remember, like I said, that's over several ventures. So if I had done like 10 ventures, and I did something very similar, that's not $2 million. That is actually going to be 20 million then. So that's really the way to think about expected values, is like, if I keep doing this over and over again, what's going to happen? We know that if I do this one time, I either lose 30, gain 20, or gain 40. If I do this over and over and over again, like let's say I did 100 different ventures, well then I'm expecting that in the end, with between my wins and my losses, I'm making 20 million. So what we're saying here is I'm expected to make on each venture about $20 million. And once again, we're looking at this long run. This would not be like 2 ventures. I'm expecting this is what I'm going to make. This would be like over the course of several ventures. Another example, so insurance is a good example of this, because insurance, you have a very, very big sample to choose from, because you have lots of people who are getting insurance. So an insurance company sells a 1-year term life insurance policy to a 70-year-old man. The minimum pay, the man pays a premium of $400. If he dies within 1 year, he gets paid back to his beneficiaries $10,000, which means that this is a net gain a net gain of 9,600 for his family, in essence, but the company loses the company's net loss is going to be that $9,600. They're really hoping that you're going to survive. Now, if what they want happens, you are going to pay your $4,000, but you don't die, the company owes you nothing, and the company has a net gain of $400 that it gets from you. So remember, this is happening over and over and over again. You're not the only person taking out an insurance policy. Several people are. People are going to die in that time period, and they're going to have to pay out. Ideally, in the end, though, they're hoping that they're making money back. So the probability that a 70-year-old man is still alive after 1 year is 97.15%, or 0.9715. So that is the probability that they gain money. The probability that they lose money. So if you die, that probability is, if you're the 70-year-old man, This is the probability that you die. So they're not really all that concerned whether you live. They're just concerned that they get their money back. So like I said, it's like to you, it's live or die. To them, it's do we lose money? Do we gain money? So if I want to figure out that expected value, I take that loss, my X, and the probability that I'm going to lose $9,600, so negative 9,600, is going to be 0.0285. Then I add to that my next X times P, that will be the $400 times 0.9715. So if we put this in our calculators, so if I take the negative 9,600 times 0.0285, I get negative 273.6. If I take my 400 times my 0.9715, then I get 388.6. If I add those together, so I accidentally subtracted those together. If I add those together, I get 115. So they are expecting they're expecting to gain $115 per loan per insurance policy. So think of this way. If they take out 10,000 policies, this is they're expected to make about this much money. I'm 1 0 off to second. There we go. I'm counting that going, there's an extra zero, I think, in here. Nope, I was right the first time. No, this is many zeros. Okay, just want to make sure I had that right before I said this. So they would expect to make, like I said, out of all these policies, so they're getting $150 a policy and they sell 10,000 policies. There's going to be some people are going to die, some people are going to live. Most of them are going to live. They're expecting to make $1,150,000. So expected values, you're thinking very long term. What do we expect to happen? Like I said, short term, it's either this or this. It's either we lose almost $10,000 or we gain $400, but long run is what we're looking at. So it's that part of the law of large numbers is we're looking at what happens if I keep going indefinitely. All right. So this one, don't think of this so much as expected values. Thinking about it's just a mean. Advancement placement or AP exams are graded on a scale of 1 is a low through a 5, which is a high. So you either get a 1, 2, 3, 4, or 5 on that exam. So we do a lot of diagnostic tests this way. We don't give you like percentages or decimals or anything like that. It's either you get 1, 2, 3, 4, or 5. You might have seen this with your I forgot what we call it, our state exam that you have to take. TSI, you see those, your TSI. The College Board reported that the distribution of scores on the AP exam in the recent year were follow. 32% had a 1, 26 had a 2, 16 had a 3, 15 had a 4, and 11 had a 5. We want to know what's the expected value. So what I'm really looking for is the mean. So it's going to be this summation of each X times its probability. So we have an X of 1 with a probability of 0.32. Here we have 2. and its probability is 0.26. Here we have 3, and the probability is 0.16. Here we have 4, and its probability is 0.15. And then here we have the 5, and its probability is 0.11. So we don't have to do this each individually. We can do this all as just one big clump, which I'm trying to do right now. And then we get a 2.49. So this is your mean AP exam score is a 2.47. Once again, like I said, it's an expected value. So I expect that when I give several of these exams, so I expect that if several exams are given, the average grade or the average score would be about 247. So like I said, you're just always thinking about this when you talk about expected value, is you think about it as in the long run.